So according to the schedule, today we have the last session concerning the seismological measurements of fracture energy and breakdown work. We have two talks scheduled, one by Rachel and the other one by Elisa Tinti. And we have some time for the discussions. In the discussion, we have already two contributions by Franta Gallovic and by Paul Selvadurai. And we will try to, I recommend the two speakers to keep the time because we will have time, we need to reserve time to the discussion. And afterward, then when we finish the session 4, I will give the floor to Men-Andrin and Chris for chairing. And we will try also to recover the presentations announced yesterday that we couldn't fit in the schedule by Georg, by David, by Stefan, and we will finish with the discussion. So I really enjoyed these 2 days, and therefore I think that since we are increasing participants, I will ask Rachel if you can start sharing your screen so that we can start soon.
I would like to point out that she has 95 slides lined up. So, you know, put on your seatbelts.
I'm not planning to show them.
All right, that's okay. 90, I bet you can get through 95. It's just a question.
Well, I perhaps could, but it might take more time than you really want to give me.
Massimo, you're in charge of the time, buddy.
Yeah, no, but okay, Rachel, let's start. Thanks.
Okay, well, thanks very much. And yes, as Chris said, I have got too many slides and too much to talk about because how to talk about the whole measurement of you know, fracture energy from seismic waves in 15 minutes is quite a big thing to do. So what I really want to do today is to give you a little bit of a background about how we make measurements, what we can trust, what we're struggling with, and where are we getting to with this kind of work. Okay, so oh, hang on, I have to click on this one here. There we go. So basically starting, I'm going to just shift this out the way. There we go. Starting with this slide from the work that I did back with Jim Rice nearly 20 years ago now. You've all, many of you are now familiar with this slide. These estimates of fracture energy as a function of slip have been interpreted in a number of different ways by us, by Vieska and Garagash, by Kay et al. Most recently. But I think what I want to focus on here is not the interpretation, but actually where these points, these measurements come from, and how much should we trust them. When we measure or estimate fracture energy, G prime, breakdown energy, whatever you want to call it, from seismic waves, what we're basically doing is trying to measure some basic parameters and then extract what we need from that. And we can do that in either of two different ways. These estimates should be made at each point of the rupture. So either we can do dynamic and kinematic modeling to measure spatially varying parameters, and this is what Eliza will talk about for larger earthquakes, or else we can just use average values for the whole rupture, maybe assuming a simple source model. And that's what we tend to do for smaller earthquakes. That's where many of those values came from, and that's what I'm going to talk about here. Basically, then the fracture energy estimate is the stress drop that we try and measure, divided by 2, times by the slip that we measure. We also need to measure the energy and the area, or the length scale of the rupture. So where do we get these from and how good are they? Many of you have seen plots of the stress drop as a function of magnitude and space over the years, and are aware that though stress drop is often suggested to be a constant, it does vary over more than 3 orders of magnitude, whether you combine multiple smaller scale studies or whether you stack large data sets and see spatial variability, but huge variation in stress drop. And the question with this is how much of this is real and how much of it is coming from simplifying assumptions and uncertainties. How much should we try and interpret? Another issue to remember here is that we make measurements of moment and corner frequency and length scale. To convert them into stress drop, we always need to use some sort of model dependent factor. So there's always a constant here that you can vary and choose. So take care when comparing values. So where do the actual measurements come from? Way back, 1960s and 70s, before digital recording and big computers, it was noticed that earthquake source spectra on average have fairly simple shapes. A large earthquake, the large area, radiates most of its energy at longer wavelengths and relatively low frequencies. Smaller earthquakes radiate their energy at shorter wavelengths and higher frequencies, corresponding to the smaller size of the source. And basically the peak amplitude in the velocity spectrum is related to a corner frequency in the displacement spectra shown here, and that can be related to 1 over the source dimension. So essentially all we're really doing is making an estimate of the seismic moment, which comes from the long period level of these source spectra and is relatively reliable because on the whole long periods are less attenuated, less messed up, it's easier to make measurements. And then some estimate of this frequency at which things break down, which is telling us something about the length scale of the source. Stress drop then just becomes related to the slip divided by the square root of the area, moment, these two. So if we've got a length scale, we can basically find all the rest of this here. Of course, we don't have data over the full frequency range. For often we're only recording at lower frequencies, at greater distances. We're limited to just seeing this bit of the spectrum. For smaller earthquakes, we need to go closer. We need to see higher frequencies. But you can see that if the earthquake has a corner frequency near the edge of the frequency range available to us, then our estimates are not going to be as good. This led to basic hypothesis that sort of I think is at the background of what a lot of us basically understand, which is that simple earthquakes is fairly simple ruptures, and that the stress release is perhaps compelled by things like the tectonic setting, with higher stress drop earthquakes in higher stressed settings and lower in lower settings. And maybe we can therefore make these measurements and learn something about the settings and the control. Of course, in reality, it's just not that simple. Every seismogram is a convolution of what's coming from the source with what happens as the waves travel through the earth and how they're recorded. Maybe things are simple, simple circular source, simple attenuation, hopefully in way the instrument, but actually the earth is more complex. When we look at large earthquakes, we see that they often involve complex ruptures, attenuation structure is complex. So when we're attempting to model the attenuation or maybe use small earthquakes as Green's functions, how disentangle this and extract the source from the seismograms, we have to remember this complexity. In practice, there's a lot of trade-offs. This was shown quite nicely in a study by Cocco et al., where they actually generated some spectra using a particular value of the attenuation and the corner frequency here in black, added a bit of noise, and then modeled it with a completely different attenuation and corner frequency. And you can see it's kind of difficult to tell the difference. This is some work I did back in 1995, where we put a seismometer 2.5 kilometers down a borehole. And we looked at the difference between the surface and the deep recordings. What does the shallow earth do to the waveforms? And you can see the difference in the two spectra here, indicating that these attenuation effects, even in just the upper 2.5 kilometers, are significant and will have a major effect on the results. They can't be ignored. So what are we doing to improve methods? We're basically going about this in two different ways. One is to do sort of large scale combined inversions to try and get source pattern site terms by using large numbers of stations and earthquakes. This is work of Adrian Oath, Dino Bindi, Peter Shearer, and many others. It's coming along fairly well, but what we've been noticing is that even though we can get event spectra quite nicely for maybe 3,000 earthquakes here, you're still left with an empirical correction that you have to put in to get these into actual source spectra. And depending on what this empirical correction is, the different green lines here, you can get fits which assumes self-similarity. You can get fits with lowish stress drop, with highish stress drop, and we really can't tell the difference between any of these. The dashed line fits all look pretty good, regardless of the model. The other approach is the empirical Green's function approach, which I've worked on more. This basically assumes you have a little earthquake, which is in there to remove all the pattern site effects, no modeling, no empirical problems like that. Unfortunately, of course, you do need a perfect little earthquake in just the right place with just the right mechanism. And what are the problems if it's not quite perfect? This is just showing you an example where we've got P and S waves, big earthquake, little earthquake, 2 spectra ratio and source time function. It can work very nicely if you have the right data. What about source complexity? When we are doing a lot of this modeling, we're fitting these earthquake spectra with simple Brune sources, but what if the small earthquakes are just as complex as the large ones? What do we mean by complexity? Well, these are some magnitude 7+ earthquakes from Ling Ling Ye's work. Here you can see the slip inversion showing 2 big blobs of slip. It shows up by a source time function, which has got 2 pulses. And then in the spectra, you can see these extra bumps, which are corresponding to the frequency content and the duration of these 2 pulses here. So if we see spectra with bumps in them and source time functions with bumps, we've probably not got a simple rupture, and fitting it simply will not work very well. And we get into this guy here trying to bash different things into a round hole. This is just a nice little example I show from some work I've done at Parkfield, where we have the benefit of both shallow and deep borehole instruments as well as surface instruments. Imanishi and Ellsworth looked at 2 magnitude 2 earthquakes that were recorded from repeating clusters. And these are their spectral ratios. The T1 P waves and S waves is very simple. The T2, the spectrum looks much more complicated. And as you go to smaller events in the same cluster, some look simpler, some look more complex. But what about if you don't, this is just one station as well, stations in a column. What about if you want to go to the stations of the shallow network? Well, now we have less frequency range because they're not as deep, but we do get to see, again, simple spectrum looking fairly similar, simple source time functions, and we can also look at azimuthal variation because we have multiple stations. For the second earthquake in this sequence here, we can see that we've got now these double pulses. We've got complexity showing in the source time functions. We can see now that we're going to get problems with our estimates because we haven't got a wide enough frequency range. What are we going to see here? And if you just use surface data for this, then we've got a narrower frequency range still, and maybe we're all right for this simple earthquake, but we're going to run into problems for these more complex ones here. Complex spectra also, and combined with limited bandwidth, also can give us systematic bias. And this was shown in this recent review. I wrote looking at some work from Jimin Wu for the Guthrie earthquake, a magnitude 4 in Oklahoma with very complex sources. I took the spectral ratio here with a fit, and then I said, well, what if we only have a particular narrow range? What if we only have the part of the spectrum we'd have if it was a small earthquake? What if we only have the part of the spectrum we'd have if it was a large earthquake? And you can see that the estimates of corner frequency and relative stress drop change depending on the frequency range you've got available to you. What about measurements of seismic energy? Ide and Barossa did a nice comparison of this back in 2001. And it's worth noting here, as we look at this huge range, the difference in magnitude of size between the original measurements and their corrected values. These corrections which are having to be applied, the problems of systematic bias are significant and can't be ignored. Seismic energy should be easy to measure. It's not a model dependent measurement, but unfortunately it requires a very high frequency range and a wide bandwidth to get it because you're integrating the velocity squared spectrum over the whole range. So as you get to high frequencies, attenuation will go from a recorded spectrum down to a attenuated one, and showing here is what you get as the cumulative sum, the actual estimate of energy without a correction for attenuation, with a correction for attenuation. So it's a real problem. And of course, that attenuation correction typically comes from fitting an omega squared model to the spectrum, or in this case, the spectral ratio from some work by Gisela Viegas. And the data content is relatively small compared to the model extrapolation. So the energy estimates are not as model independent as we'd like. I was enjoying the work presentations yesterday, and I was looking at this, for example, the results from Greg McClaskey's experiment, and I was just thinking, look at all those sensors. You know, this is what you're doing in the lab. This is what we're struggling to do with large earthquakes. And for smaller earthquakes, you know, it's getting to situations like this where we have relatively few recording instruments. They're a long way away and everything is buried in some stuff we don't really know what it is. So what can we believe? What can we measure? I tend to treat measurements like this as pretty approximate with large uncertainties, but I think we are doing better at making some other measurements. One thing I've done is to look at earthquakes in a range of different tectonic settings. This is some work from New Zealand, where we had several sequences that were both within the subducting slab, above the subducting slab, and even on the subducting slab. And the results of this analysis for stress drop using empirical Green's function analysis basically showed that the range of values you get in any one setting, here red for Ekatahuna or blue for Cook Strait, are much larger than any difference between these different settings. And that variability within the sequence really seems to be real. For example, let's consider these two events here that were well recorded by multiple stations. Here's just an example showing you some actual data, the P waves and the S waves as independent measurements, large, small. Spectra, spectral ratio, source time functions. These earthquakes are different. We have multiple empirical Green's functions. We're doing this stacking using them with different values of cross correlation, different combinations, and you can see that the stack ratios for this event here have got higher corner frequencies, higher frequency content, shorter pulses than the ones for this event here, even though they're quite close together. So I think this, they're actually these two events here, so they're only a few kilometers apart. So by looking at both P and S waves to see if we're getting some similarities, yes, high, yes, low, then that gives us some independent estimate. I think we are seeing real variability. Another recent study that I mentioned is one by Colin Pennington, who looked at the Prague earthquake sequence for his PhD. In Oklahoma. He compared multiple different measurements of stress drop using different approaches, P waves, ratios, modeling, S waves. He compared them to previous estimates, very wide variation in the actual measurements. But when we actually plot the corner frequency per event against a reference value, we can see that there is similarity. We are seeing real trends, the stress drop also. So that basically earthquakes which are high stress drop in one study tend to be high stress drop in all of them. So we are getting some useful resolution here. I've been revisiting earthquakes at Parkfield.
Rachel, it's Chris. Sorry to interrupt real quick, but 15 minutes has passed, so it'd be good to try to wrap up.
I'm getting quite close. Earthquakes at Parkfield, again, magnitude 2 and a bit. We're seeing spatial variation. These are multiple earthquakes recorded at different azimuths. You can see the variation in the source time functions. You can model it with directivity, actually see that. You can see source time functions with sub-events. Dense recordings at the Lasso Array in Oklahoma, recently by Colin Pennington, where we have thousands of stations. You can see multiple patches of slip down to magnitude 2.5. So we've definitely complex earthquakes at small scale. And a recent large scale analysis at Parkfield, again, another example I'll show you, which used borehole data compared to the previous one by Peter Shearer and colleagues, which used only surface data. So we've got higher frequencies. This was the earlier study. This is the new one. Again, now we are seeing very variable stress drop with space, very small scale variation in the values of stress drop, which is completely independent of whether we're in a creeping or a locked zone. The spatial variations are much larger than the temporal variation. So lastly, we're trying to address the variabilities here by organizing this community stress drop study through SCEC, where we're trying to get multiple people to measure the same events to see if we can get some agreement and sort out the real variability of earthquakes from just the model measurements. The preliminary results are showing us we've got a lot of scatter, but these are very preliminary and we're working on it. So in conclusion, thank you. I think basically, you know, we need to interpret these measurements with care from these small earthquakes. There's a lot of uncertainties from the data quantity and quality, from the assumptions about attenuation, correction, and source model. Ongoing work to improve measurements is making progress, and we are starting to be able to see smaller earthquakes in more detail. But quite what measurements we should be making and how we can use these to help with getting at things like fracture energy and constraints on the source processes is something that I'm actually open for discussion about. So thank you.
Excellent.
Thank you, Rachel. Excellent.
Sorry about the timing.
No, you did marvelous. So are there questions or comments to Rachel? Let's see. Jay, please go ahead.
Okay, very nice talk, Rachel. I've got a really, really stupid question.
That's okay.
Okay, we have an earthquake that starts out with a large stress drop and then very quickly hits a barrier and stops. Okay, so the real stress drop, if we think about it, how does that even relate to the size of the earthquake? I mean, there's no.
Yes, I think we do need to think quite carefully about what we're actually measuring. And one aim of the stress drop, the community experiment, is actually to bring together different communities, because what you're wanting is actual details. You know, what do you mean by stress drop? What do you mean by, you know, you're after the dynamics of the rupture. Whereas stress drop to a lot of the seismic community is really just a sort of moment independent parameter, giving you an idea of the level of high frequency shaking for ground prediction. So, and they're not the same thing. They're certainly not the actual stress drop. So we've got some semantic problems, and we've got different needs of different communities. So yes, I mean, you know, my concern is that if we go in and we start looking at every magnitude 2.5 in great detail and looking at the complex rupture and trying to map it out, and there's an awful lot of magnitude 2.5 earthquakes. And how do we compare those, and how do we put that together, and how do we characterize those with some useful number for the kind of work you're doing?
So a lot of the uncertainty that you see could conceivably be because of large variation of heterogeneity, fracture energy, whatever you call it. So they all start out, you know, some start out with a boom, some start out, you know, just barely, and they stop, and then they seemingly have the same magnitude. So.
Yeah, they would have, yeah, I mean, two earthquakes, if they release the same amount of moment, then they will have the same magnitude. So in some ways, all we're doing here is basically saying, if you release, you know, if you have a certain magnitude, that's the total, the area times the slip, the total moment of the earthquake. And then you basically just get a duration estimate. If it's a short duration, then you've got a lot of high frequency energy, buildings fall down, and we would say it was high stress drop. It's small, it's short. Maybe it was just high rupture velocity. If it's, you know, if it takes longer to rupture, then it's a larger area, maybe, or maybe it's just a lower rupture velocity. It's going to release less high frequency energy, which is important for ground motion. But to get into the details of why, you know, I think basically Elisa's talk will help us a little bit with that. And maybe we need to try and do that kind of work on the small earthquakes, except we don't have the resolution.
Thank you. So Chris, you have a question, and therefore we move on. we keep the. Please go
Okay,
ahead.
I raised my hand. I raised my hand simply to make the point that there are 108 people, and we should encourage everyone to participate and ask a question or make a point or something, especially early career people. Thank you.
Yeah, thanks, thanks, Chris. Okay, thanks, Rachel. So if we don't have other questions, or if questions will come in mind, keep them for the discussion of the session. Elisa, if you can share your screen, you can start your presentation, and we will let you know when you.
And Greg McClatchy, if you want to make a point while she's starting, go ahead.
Yeah, I just wanted to sort of follow up with Jay's question. So Jay said, let's say an earthquake starts out and it has such and such a stress drop. But from a seismological point of view, this quantity stress drop is something that exists for an earthquake that is completed. So, right, it's not necessarily exactly related to the dynamic stress drop that is occurring during a rupturing earthquake. So you could have an earthquake that's rupturing and has a huge dynamic stress drop, then it hits a barrier or something, and there's actually a stress increase in the location where the barrier is. And the stress drop that a seismologist is going to try and quantify is sort of a spatially and temporally averaged quantity that's related to all of that, right? So we got to be careful when we say stress drop, that the seismologists are going to think of this as a spatial average of an earthquake that's completely finished.
Yeah, correct. A very important point, Greg.
Yes, yes. I mean, the measurements we make for the small earthquakes are just these gross averages. I think as we see Elisa's talk, you will see, try taking that down to the small events, which are also complex ruptures.
And so just like saying a little bit further, an earthquake that really did have a huge dynamic stress drop or a large, stress excess that's fueling the rupture or something like that, it may propagate out further into unfavorably stressed regions or go further through a barrier, and that may end up sort of compensating for so that in the end of the day, the stress drop is, about a few MPa, just as we see. And so that may be one of the reasons for this invariance of this stress parameter.
That would be a great topic to come back to. Thank you. Great.
Thanks. Elisa, please go ahead.
Okay. Can you hear me?
Yeah.
Okay. So I'm happy to present some results about breakdown work and fractal energy from a seismological point of view, following the discussion started by Rachel. So, next slide. Okay. So I will start my presentation starting from the definition of fractal energy and breakdown work, first of all. And I want to emphasize right away what we do as assumption hypothesis to compute breakdown work or fractal energy. So first of all, we have to model the event or as a simple circular source, as Rachel already presented, or an extended source that can be homogeneous or heterogeneous in space, and that our estimates of breakdown work and fractal energy can be derived from kinematic modeling or dynamic modeling. And if we assume dynamic modeling, we have to choose a constitutive friction law that can be deep weakening law, linear or not, latent state, exponential law, velocity weakening, that differently describes the evolution of shear stress with full motion. So let's start from the definition. The breakdown work is defined only as the excess of work, that is an energy, in any case, an energy density, over some minimum traction level achieved during the sleep, while the fractal energy is defined as the energy per unit area that is required to extend the crack. That is the amount of energy necessary to maintain an ongoing rupture which propagates on a fault, and is associated with the area below the shear traction curve and above the residual stress level that is assumed constant in this kind of linear friction law. So the term of fractal energy has been literally used to refer to an elastic dissipation that occur on the crack tip. This is what Massimo also was suggesting before, to understand the difference between the energy absorbed at the crack tip or behind the crack tip. And in any case, this scalar equation show you an integral between 0 and the critical zip weakening distance. While more in general, the breakdown work has been defined as a scalar product of two vectors, the traction evolution as a function of time, less the minimum traction reached during the slipping phase, times the velocity, that at the end is always the area below the traction evolution. And the integral is between 0 and the breakdown time, that is the time in which we reach the minimum traction level. So this can recall also what Onaka was defining when he's trying to define his fracture energy in his experiments, because breakdown work includes also the energy lost during the slip hardening phase that can occur. And as Onaga said, there is a phase of non-elastic deformation during which microcracking develops before the macroscopic shear failure. So in this case, the breakdown work can be more general as a definition. And following the definition set, we have to say that after the minimum traction is reached, we can see in our models also some energy spent between the critical zip weakening distance and the final zip. So for this reason, in 2005, we defined not only the breakdown work, but also the energy spent in this time. So that is called the re-strengthening work. And together with the breakdown work represent the excess of work that is the area below this curve and above the minimum frictional level. And these recall also what Ellis and Karagash presented on Monday. I'm happy to show also these sketches that has been done by Paul Spudic almost 20 years ago when we were discussing how to partition the fracture energy, heat, other dissipational processes, and we were discussing about seeing some evolution of traction as a function of zip that can change in time because different physical processes can happen at different length scale or time scales. So we were discussing about how we can partition the energy spent in heat, in fracture, and so on. So, which is the true partitioning between the panel C or panel D in these figures. At the same way, also, if we think about the power law, we were laughing about saying that in this case, it seems to be that large event can dissipate less heat respect to small event that can have this kind of higher area below the frictional level. So what we have to do when we want to determine traction versus slip evolution for natural events that we observed and we record with the waveforms, we have to start from some models. So or simple circular source like Rachel has already presented, or finite source that have to start from kinematic models or dynamic one. So if we start from kinematic models, we have to choose a priori the slip velocity function on our fault and for our rupture models. And we want to fit waveforms up to 1 Hertz, more or less. And in this case, we have no physical constraints. So kinematic models can fit very well your waveforms, but has no physical constraint because you cannot ensure that this model can break spontaneously and reach the final magnitude as the real events. While if you model with spontaneous dynamic modeling, you have to choose a priori a full constitutive relation. You can fit waveform always up to 1 Hertz, but in this case, you have to assume a physical constraint. So when you choose a constitutive law, you're choosing the physical processing that are acting on this full plane. In any case, you can find a traction versus slip curves. In one case is an output of the models. In the kinematic models, you have to pass through an equation that is called the elastodynamic equation, in which you can relate the local stress change with the rupture history on the fault plane. So the first important result has been done by Guattari and Spudic, in which they models a target event like Imperial Valley, in which they propose two extreme models. One, model A, in which you have a slip distribution very similar to model B, a stress drop very similar to model B, and the fracture energy in the bottom panel very similar between the two models. while the strength SS, that is the stress between the peak yield stress, the yield strength and the initial stress, is very different, and also the critical slip weakening distance. So at the end, the area is the same because we are changing the breakdown stress drop and dynamic, the critical weakening slip. And they say that at the end we have a trade-off, because if you look at the waveforms, these waveforms are for both of the models are identical, and we are fitting these waveforms up to 1 Hz, 1 Hz and a half. So these are the range that we are looking when we want to invert for kinematic extended models, or we try to invert also for dynamic models. So they concluded that estimates of fracture energy, in this case, the area below this traction versus slip curve, is the only reliable quantity respect to the DC or the breakdown stress drop. Recently, Franta, that maybe presents something later, tried to invert with the dynamic raptor inversion for a magnitude larger than 6, for example, a Matrice earthquake, and they try to find the distribution of the initial stress, the DC, the breakdown density, with giving an average estimate that fit what we see when we average the breakdown work and the slip on the fault plane. When we use kinematic model, how we can infer information for the dynamic one. So there is an equation proposed by Fukuyama and Madariaga, in which you can see that the traction change in each position on the fault and at any time can be due to the relation between the punctual slip velocity and an integral that represents a kernel of points that are slipping on the fault plane. So this kernel is really different if you are having a rupture that is a crack-like or a pulse-like. So is important or not, depending on how many points are slipping during the breakdown phases of these local points. So starting from a kinematic model, you can reach and can have information of your dynamic corresponding modeling on the fault plane. So many papers have been using this procedure. So they use the input, the rupture history, and the output, you can see the shear stress history, and so you can compute the fracture energy of breakdown work, on any case, an area below the shear stress evolution. So this is an example for the Imperial Valley, in which the authors of, that proposed these kinematic models use as a slip velocity a cosine function, very smooth. So at the end, you can see that for different points on the fault, if this is the slip velocity on the fault plane, this is the traction evolution as a function of time, and this is the traction evolution as a function of slip. So your traction versus slip results very smooth, and at the end, the critical slip distance is almost 99% of the final slip. And you can see also that the critical slip weakening distance is very similar to final slip, and also in shape, not only in the amplitude. These are another example for Lander earthquakes, in which the authors use the tangential function, and again, the energy that you can measure below the traction curve as a higher DC, and you can see this is the distribution of the breakdown work, and this is the distribution of the final slip. If you use another model, in this case, Cirella et al. Has inverted the strong motion data and geodetic data by using a Joffe function. So in this case, because they used a short acceleration time, the corresponding traction evolution show a DC that is a small percentage of the final slip. So you can have this kind of curve that seems to be seems to have a smaller DC. And in any case, for this kind of heterogeneous distribution of slip, rupture velocity, rise time, and so on, you will have a very heterogeneous distribution of traction as a function of slip in the fault plane. Make an average, as Rachel was saying, so it's difficult to think about an average, a point for this kind of large event. We can see some relation between this energy as a function of seismic moment, but this point represents an average of this big fault plane. So how this average is done can change a lot this kind of relation. For example, if you see the stress drop on the fault plane for the L'Aquila earthquake. These other panel represent the area when you select only the portion of the fault that has a minimum slip. So maybe some area in the fault cannot be well resolved. So this change the average of stress drop and the average of your fracture energy of breakdown stress drop. So at the end, this is what appears when you try to put the breakdown work as a function of seismic moment. If you consider, for example, the estimate that change as a function of the area in which the slip is higher of a percentage of something, or an average of a maximum slip, and so on. So you can see that you can have an increase of the breakdown work as a function of seismic moment, but also you can have this variability, uncertainties, I don't know how we can call this kind of variability in our models. I want to show you that if you use, for example, very simple models in which you impose the slip velocity function, and you want to retrieve the constitutive behavior, you can see that the DC parameters and the rate of the weakening can change a lot if you change this slip velocity function. That is one of the more difficult parameter to constrain on the dynamic model, on the kinematic model. Sorry. And in any case, the area that you can compute can be almost similar in this model that is homogeneously distributed on the fault plane. But these estimates of breakdown work can represent the energy absorbed close to the rupture front when DC is very small with respect to the final Z, or can represent the energy absorbed on the tail when DC is almost close to the final Z. But also this ratio depends also on the relation that you have between the cohesive zone, so all the spatial cohesive zone, so all the points that are in the breakdown phase, and the rupture velocity of that event. Okay. Again, a very simple model in which you can see that if you have a different acceleration phase for the same slip velocity function on a very homogeneous model on the fault plane, you can have a very different traction versus slip curve, and maybe very similar breakdown work energy, because you are decreasing the peak slip velocity and you are increasing the DC, or you are decreasing the peak slip velocity, you are increasing the breakdown stress drop. This can be do also when you maybe are able to retrieve model for higher frequencies. So if we constrain our model in a small frequency range, maybe these estimates on the peaks, the velocity can be affected by our choice. So one important thing that we have to do is, because kinematic model can give us some information on dynamic parameters, we want to understand if these kinematic models are dynamically consistent. So if the parameters that we retrieve for kinematic model are able to sustain a spontaneous rupture propagation. And this is what we have done last year with Alice Gabriel and the co-author, starting from a kinematic model of North earthquake, and we try to fit the waveforms, try to reproduce the kinematic models, and to find the best dynamic models on the fault plane. In this case, we used a linear slip weakening law, an heterogeneous DC that has to be proportional to 10 or 30% of the slip. So we can have DC values that range between 10 centimeters to 19 centimeters for North earthquake. And we have to assume an heterogeneous distribution of the yield strength or initial stress to have this kind of heterogeneous parameters on the fault plane. And at the end, we can have an average estimate of the what we call breakdown work, but in this case, because we are using a linear slip weakening law, is fracture energy as definition, that is around 0.7 megajoule over meter square.
Elisa, you have a few minutes to
finish it. So if we consider homogeneous distribution, we can have and the distribution of fracture energy that can be 10 times larger if we use similar DC parameters and homogeneous distribution of dynamic parameters. So putting together the results on laboratory experiment, high friction, low, slow stick slip events, large sample by Kammer and McCluskey, pseudodynamic modeling, spontaneous dynamic model for magnitude 1 or 6 or 7, you can see that this increase in breakdown work seems to be very confirmed, with a similar power law relation. I can put from the literature a result from Selvadurai and Biesca and Gagash, and Aretosini try to put all this data together in the literature to see what we can see from smaller and larger events. And as a summary, we can say that the seismological result cannot provide any information on the governing microscale physical processes, but we can also only estimate the macroscopic frictional work. That the breakdown work is a reliable parameter, while DC for our models is model dependent. That we will be like a dream to have information on the real velocity, slip velocity function, because can give us information on the dynamic parameters. So it's a challenge. And the pseudodynamic model cannot demonstrate if the energy absorbed is really available, while spontaneous dynamic model are the only way to verify if this energy expended was actually available. So in any case, we depend on the assumed constitutive law. And in any case, spontaneous dynamic models for observed event give fracture energy estimate consistent with the breakdown work estimate from pseudokinematic models. These are my questions, so that we can share during the discussion if you want, about the frequency, the energy partitioning, the physical mechanism that control this evolution, and how we can determine if these energy are spent at the crack tip or behind. And these are the summary that is my last slide, in which I have summarized what we have seen in these days. Thanks.
Thank you, Elisa. Excellent, thanks.
Very nice.
Very nice. So are there questions to Elisa before that? So, okay, Rachel, please.
Okay, just one question on the topic I always seem to go on about, which is resolution of the data. Lisa, whenever I always worry that estimates of D sub C and breakdown work and all of this kind of thing, are going to end up being larger because you are looking at large earthquakes using, limited frequency range. I was wondering, have you ever taken a big earthquake for which you've got really good data and done the measurements and the modeling using different limited frequency ranges to see, where they're going to 1 hertz, where they're going to half a hertz, where they're going to, 5-second period? How does that affect your results?
The answer is I don't know the right answer, and because the range is very small, up to 1 hertz. So if we go up to 0.1, at the end you are able to see a point source instead of an extended source. So we are not a lot of choice in choosing this kind of frequency interval. So I don't
even for the can you not do something with a magnitude 8 or 9?
I didn't do.
Okay,
I'm sorry. Yeah.
Georg?
It's entirely possible that I missed the point. I'm still trying to digest this here. Lisa, thank you for the presentation. But so the way you define a breakdown work basically boils down to something that's a little bit larger, than your fracture energy. Yeah, because it includes this part, if you follow Onaka, from the initial stress to peak stress, and that's probably related to some, hardening in the material or so. Now, it doesn't explain, though, these orders of magnitude difference that we observe between the laboratory and your field measurements, seismological measurements. So it doesn't really contribute to explain that, right?
I think that the hardening phase, I don't know if this is the more difference between fracture energy and breakdown work. I think that breakdown work can be similar to fracture energy. Depends on how big is this critical slip weakening distance. So breakdown work is an energy spent above the minimum. Doesn't pretend to say.
Let's talk about a factor of 2, okay? But not orders of magnitude. So we are going from, you know, tens to hundreds to 10 to the 3 power 3 joule per square meter for measurements that you perform in the laboratory, to what you have here is like 10 to the 6 or even higher. So a factor of 2 is unimportant, I think.
I understand. If you want to run, for example, a magnitude 1, not magnitude 6, for example, in this case, magnitude 1, I made an extended dynamic spontaneous fracture, and I have seen that I need this kind of breakdown work that is, in this case, fracture energy, that is 3 orders larger than the lab, to allow a spontaneous rupture on 20 meters square of area. So as definition, if you use also slip weakening law without thinking about any unelastic dissipation of fault, nothing, saying everything is elastic, I have a magnitude 1, how I can allow a spontaneous propagation on 20 meters over 20 meters square. With this kind of DC, for example, is possible at a depth which we have 30 megapascal of normal stress, something like that. And I obtain a fracture energy that in this case is the same value, around 90 kilojoule over meter square. So this is not coming from a big earthquake, kinematic, pseudodynamic modeling. Everything is very simple, and I cannot think about a magnitude of fracture energy of the order of joule over meter square in this case too. So maybe our definition is different at the end.
Yeah, and just a small contribution to that, Georg. The issue is that in any case, what we observe with seismology is similar to what we observe in the lab when you sleep at a meter per second. So the issue here is that sleep velocity is a meter per second in this, and the fact that during the breakdown stage, you have the entire evolution of the sleep velocity, it does matter. So David, no, David disappeared. So.
I'm sorry.
No, I just wanted to very quickly to the beginning of Georg's question about the hardening. If we define the fracture energy as the thing that governs the rupture, then this hardening doesn't matter. It's really just there. Whether you start from the top and you go down, or you go first a little bit up or down, doesn't matter. It's still the fracture energy. So that clearly doesn't distinguish what fracture energy is or isn't. Just to clarify that maybe.
Yeah, I agree.
I agree.
Yeah, but in any case, the point to me is that if you have this hardening, this means that before the breakdown stage, you have some slip on the fault or in the near tip. It even might be coalitions or microcracks that you have at the tip.
But this is still the breakdown part. I would just include that in the breakdown part.
Yeah. Okay.
My interpretation, sorry.
Okay. So there is, I see that there is a Wojciech.
Yes. Can you hear me?
Sí.
Yes.
Okay. I have a comment to what Elisa just was showing. Just mentioned that seismic data probably provides no information about the microphysical processes of leading well occurring during the earthquake at microscale. I'm not quite sure. I'm not convinced from your presentation at all if it's true. The fact is that seismic data are very specific, but anyway, they should contain information on this microphysical process.
For sure.
Inferring this information might be quite difficult. Maybe it's impossible sometimes because, you know, inverse problems are quite often non-unique. It might be, but this information should be. And also, there is one. Okay. So
maybe my English is not perfect. I will say that we are not able to retrieve.
Okay. And there is a big chance also that we are looking at the wrong features of seismograms. Okay, we are looking at how seismograms looks like in frequency domain, in time domain, but one can look at a completely different features of seismograms, some cross correlation parameters, or some so many others, much more complex. And then it would be very interesting to see if such a more complex features of waveforms does not provide deeper information on the physics. That's what I wanted to say. Thanks.
Thanks, Wojciech. Rachel and Nadia. Rachel.
Oh, yeah, I'm just thinking about resolution again. In what you're looking at here, Elisa, is you've got different D sub C and different breakdown energy and everything for different magnitudes. Now, obviously, we can't use a D sub C of 30 centimeters to model a magnitude 1 earthquake because it doesn't have that much slip.
In fact, yeah.
Have you tried it the other way round? If you constrain the parameters for the large earthquakes to be the same in terms of the small breakdown work and small D sub Cs for the small one, can you actually model the waveforms for the large earthquakes?
So I show this very simple example in which I use the same fault plane for the North earthquake, in which I assume everything's homogeneous. So DC distribution that is constant in the two faults cannot be smaller than 0.5 meters. Otherwise, you can have a super shear rupture. Even if you change some breakdown stress drop, you cannot find a combination in which you try to have a spontaneous rupture with a subshear rupture and so on. So, but if you increase the DC too much, or you are not able to propagate in the whole fault, or you have at the end a very high fracture energy and at the end also an higher magnitude with respect to the 6.5 that is your target in this case. So it's not so simple to find a condition in which your parameters are similar to the smaller. I don't think that exactly is a percentage of the final slip, but we cannot say that smaller DC can be in the smaller events and larger events. So it's not so simple to constrain.
What about if you add heterogeneity?
Yes, this is what I have done here. So I can have, I have to, how you say, play with numbers to allow slip patches where the kinematic models found this kind of zip. And but again, if the DC is too small, you can have super shear in the slip patch. If it's too much, you prevent the rupture to propagate. So it's a play with the numbers, and this is my best in this case. So you can see that the DC is again larger respect to the smaller events, that you cannot have something larger than 10 centimeters because the magnitude is small.
But of course, the slip model you're starting with is a smoothed model.
In this case, I start from a spontaneous dynamic model and from linear slip weakening law. So if I change the constitutive law, maybe I can find a different range of this kind of DC parameters. But it's a big toy model at the end.
Thanks. Nadia.
Hi, everyone. Sorry, I wasn't attending much of the workshop because of some family conflicts. Thank you, Elisa, for a very interesting talk. I have a question or comment to Elisa, and also a general comment if there is a time at some point. But so to the question that Rachel was asking, Elisa, if the slip weakening was not linear, right? Mm-hmm. But rather slip weakening was of the type that Rice and Abercrombie advocated, right, where there would be a very, very sharp slip weakening at the beginning and then more and more gradual, then you could reconcile the two, right? You could have a very small effective D sub C for small earthquakes and much larger effective D sub C for large earthquakes. And that would be one way to have a single relationship, right, which would have both.
Okay, and I agree with you. And what you can find in the literature that all the people that try to invert or find the parameters from dynamic models for the real events try to use linear slip weakening law only because we know that what is static friction, what is dynamic friction, and what is the breakdown stress drop. We can use power law, any other kind of constitutive law. So in that case, we can play with these numbers, but we need some reference. So this is why we use linear slip weakening law. I understand we do that if I use, but in that case, if I use power law, I'm assuming that some physical processing are occurring on this kind of magnitude 7 or 2 or 1. But I agree. But we need
Thank
some
you.
reference also in these parameters for the real events, for sure.
Yeah. Also, I just wanted to make some general comment, but I'll wait until maybe questions to Elisa are exhausted. So.
Yeah, Nadia, because we have now time for the discussion, but to open the discussion, I would like to ask Franta and after Paul to give their short presentations. Therefore, we can have overall finalize the discussion on the session. So Franta, if you are ready, yeah, I kindly ask you to, yeah, please go.
Okay, I'll just throw in, to keep ourselves on time, these are going to be 2 or 3 minutes, okay?
Yeah. Okay, so thank you for allowing me to talk here. In our works done together with Lubit Savalentova, Jean-Paul Ampuero, and Alice Gabriel, we concentrate on the so-called dynamic source inversion. So as it was introduced already by Elisa, in this case, we somehow get over this intermediate step of finding a kinematic model, which is always spoiled by some constraints, like stabilizing constraints, like smoothing and so on. And we go directly to the parameter to infer the parameters of the friction law. So we assume some friction law, as already discussed. The simplest one is the linear slip weakening. Then we run the rupture simulation, calculate slip rates, waveforms, and then we optimize directly the friction law, or the dynamic parameters on the fall. And we had several applications to the Amatrice earthquake, but also to the Elazig earthquake in Turkey, which I would like to mention here. It was magnitude 6.8, and this is how we can fit, because I have only 2 minutes, this is how we can fit the data, the seismic data. We can see that the station distribution is almost perfect. So we are fitting the data basically as well as in the kinematic models. And here is the resulting model for this 6.8 earthquake, the rupture propagation. So you can see that we were able, it's painful work, but it can be done. We can, let's say, optimize the model to fit 20 seconds of rupture propagation or moment rate function or seismic data. And we need this kind of complex model. This is what I would like to stress here. You can see that it consists of several stages, starting with rupture propagation in one direction, then changing the direction to the opposite one. So it's like a boomerang like rupture propagation. And it consists of these episodes. And here those are the parameters of the models, how they can look like. You can see it's almost 60 or 50 kilometers large rupture. Those are the main, let's say, kinematic parameters like slip, rupture speed, but the dynamic models, dynamic parameters like stress drop, initial stress, DC, friction drop, and also fracture energy, which is here in this rectangle. And you can see that, especially because we concentrate on the initial stress, DC, you can see that they are really highly variable. And in the paper, we discuss several interesting features, or we think that were interesting features. But I would like to concentrate on the pulse, on one of the episodes that we have seen really at about this position at about 40 kilometers along the strike, because this part is, I would say, very well constrained, because it happened, after like 15 seconds or 10 seconds of rupture propagation. So the rupture front contains all the information from the previous history, and yet we are able to fit the waveforms up to 2.5 hertz. In this case, you can see that we fit nicely the directivity pulse. And what is interesting, I think, on this feature is that after the rupture runs through small fracture energy areas, let's say, it's still 10 megajoule per second square, but it is able to rupture over this high fracture energy part of the fall with large stress drop, because we need large pulse here. But we also need to fit the duration of the pulse. We need a relatively modest rupture speed, about 2.5 kilometers per second, still with large slip. And all these parameters that are somehow required to fit the waveforms to this, say, to this extent. So I would say that in these dynamic inversions, they are really very complicated, very hard to do. But I think that we can, since we are jumping over these kinematic models, which are, as I said, spoiled by or as Elisa also mentioned, spoiled by, for example, by the smoothing or the choice of the rupture slip rate function. Here we are basically stabilizing the inversion or constraining the inversion directly by the friction law and by the dynamic modeling itself, so including also the elastodynamic equation, which is also part of the dynamic modeling. So this is what I would like to stress here. And if you have any questions, I would be very happy.
Thank you, Franta. Just one clarification, if you can confirm. When you speak about rupture front, for you is the propagation of the slip velocity pulse, correct?
When I'm talking about, sorry, I didn't hear about the
when you interpreted your model and you were speaking about rupture front, for you the rupture front is the propagating slip velocity pulse.
It depends what I'm somehow talking about. I mean, if I'm talking about the rupture velocity, then yes. But
no,
for example,
sure,
the fracture energy contains information also about the pulse and everything.
Yeah. Okay, thanks. So,
Massimo, you're muted.
Sorry. Are there questions dedicated to Franta? Okay, if no, we can keep them in the discussion. So, Paul, can you show your slides so that we can move and finalize the discussion of the session?
Stop sharing.
Yeah, thanks, Franta.
Yeah, and Franta, that was great, and it'll ties in some really nicely with some things that Jay Feinberg brought up at the very beginning. So we can come back to that in the general discussion in a few minutes.
Hi, everyone. Can you see the screen?
Yes.
Yes. Okay, great. Okay, good. So I'll just give you some insight on how we inferred G prime from AEs in the lab. And I say inferred, and this goes to what Greg was saying earlier, that this is a way that we apply a model that they use in the field, typical shear crack models. And you can see, and Rachel was saying before, oh, I really like the lab because you can get so close and it's very easy to understand. Well, we can also look at very small things in the lab, and we have to be far away to do that too. So I'll try to summarize what we did. There's 3 studies on this. It was a direct shear friction experiment, which you see here, and we loaded it up, and it had a stick slip event. Prior to the stick slip event, there was acoustic emissions that were generated from the interface. These were shear emissions, and in this last study, I tried to apply circular shear crack models to understand them better. So if we look at some of the waves that or voltages that we infer from our sensors, prior to the stick slip event, we were seeing these small impulsive events. We isolated P waves and S waves. This is similar to what Rachel was showing of how you apply the simple shear crack models to what they're seeing in the field when they're far away and they can't get very close and measure it directly. We can see the P wave, we see the S wave, and what we did is just take the Fourier transform. I'm not showing it, but these sensors were calibrated, and that's a must if you want to apply these omega models. So we fit an omega model to the spectrum. You can see that this is a displacement spectrum here, and we can get various estimates of omega and the corner frequency. And using the simple shear crack model, we can estimate the M0 and the source radius. And again, Rachel was saying this K here is model dependent, and there's no real clear way or rhyme or reason of how this is applied at medium scale, or let's say underground rock lab scales, laboratory scales, or small regional field scales. We can also estimate the slip using this simple relationship that we all know. And again, the stress drop is this average term, the Eshelby stress drop, where we dislocate the circular plane with that slip and try to find out how much stress is required, shear stress is required to do that. the results that we see and what we're looking at here with the calibrated acoustic emission sensors was clusters of what's called attoseismicity. I just went one scale lower than Bill Ellsworth's definition for micro, nano, pico, femto. We're at -6 to -4. And atto would be around -6 to -9. So that's what we're seeing here on these calibrated sensors. I've applied the source model, and you see that these apparently have very low slips for this shear crack model. 11 nanometers to 110 nanometers. So these are some of the estimates from these simple models. And what I tried to do is compile multiple studies where they employed this model at Underground Rock Lab, which we're interested in. We do research in Underground Rock Labs here in Switzerland. Also in other lab experiments that had calibrated sensors, and studies that range up to not exactly where, some of them include what Elisa was showing, but a lot of these were just the Brun source model applied, and this is the Abercrombie and Rice scaling that we saw. And for some reason, whether this is something that is due to ray paths or side effects or instrument responses, we see this different scaling. And what I'm learning here is that maybe these aren't the right models to capture the proper fracture energy. And just to show people what I did was I also filmed along the interface. This is something that has been published in the first study and is very qualitative, but I tried to apply this photometry. And in these regions, what we saw was you're seeing the interface is blue here, and I'm shearing, and this is a stick slip event happened at 400 microseconds. It's going to replay the video. But if you focus, there's these tiny patches here that become discolored, and I don't know what this means. It has what we see is between frame to frame. This is a camera recording at 60 frames per second. They disappear, and in some cases they were co-located to the emissions. And in this large disparity that unlocked or something happened right before the stick slip event, which is when it goes completely blurry, there's some change in the amount of light transmitted through the asperity. So we're trying to infer these circular shear models to regions that maybe have high complexity, that evolve quasi-statically, and the release of these models when we're inferring, sorry, I'll go back here, when we're inferring these fracture energies may be difficult to do at scale. We're seeing even in the lab, when we look at these things, it's not so simple as these simple shear crack models. But yeah, that's all that I have for this little presentation.
Thank you, Paul. It is extremely important. It's extremely important to see that if we process seismological data in the lab at the scale of magnitude between -6 to -9, we still see the scaling with sleep. So I think that, this is a very important contribution, even if coming from the lab is a very important contribution to the discussion for the fracture energy. So I see Jay and Georg.
Yeah, just a quick question. It looks like you can make a really nice quantitative comparison between different ways to measure fracture energy, but why don't you just compare it to kind of like what we've been doing and Greg's been doing and Fukuyama, using a strain gauge to look at the LAFM waveform. Get the fracture energy directly and then compare it to what you can surmise from acoustic emissions.
That would be the ultimate way. That I think that's one thing that we have to look to do. So I just put your experiments here, and you're seeing these precursory slip fronts, and then you apply the fracture mechanics approach to it to estimate G here. And this is, I mean, I'm not sure exactly how much slip was inferred from when you look at the interfaces, the pulses go through and completely unlock. But on the scales that we were looking at with those tiny asperities, in my experiment, when these are unlocking, we see all these events is quite complex. This is not appearing on a similar scale, and the amount of slip, I think, is very, very small if we think of it just in terms of the moment that's released. And use Aki's relationship between moment and slip. It's very small. So these are nanometers, and I'm wondering if there could be better ways to do this. And I encourage the people that have continued to work on the PMMA interfaces to maybe look for these as well. I know there's still people doing this, but measuring these small events and the local breakdown of strength here, let's say, it doesn't appear on my slip sensors. I'm doubting the resolution on the strain sensors off fault also plays a role in the sensitivity that you can see on fault. So I don't know if it would show up in these typical ways that you're measuring it here with the strain gauges. It would
I would suggest, we can talk about it. I would just suggest using larger events. It looks like you're looking at single asperities that are slipping, which is interesting, but it's I guess a different question. It's not looking at the interface as a quasi-continuum, but I don't want to monopolize the conversation. So
no, that's a very good point. I think better tools and more thinking out of the box for how to measure maybe this process at a very local scale would be something that's interest to the community. Can't get it to start.
Yeah, but I think, Jay, it is like looking at a micro earthquake, right? Yeah, you don't see a macroscopic fault slip, but you're seeing something and trying to infer what does it mean?
So like I said, Rachel says you're so close in the lab, but we can actually be far away in the lab too. So
yeah, and that is exactly what we are going to do in FEAR. Be able to have with the same sensor in the lab and in the fault to try to measure and to compare what we measure and to see if these pico earthquakes are complex or simple, as Rachel was pointing out. So Georg.
Yeah, I'm asking myself whether this outcome is not just a, sort of a natural outcome out of the way we interpret this this model. So following what Federica and David, I think yesterday proposed was that you would have, a fracture component that's associated with the rupture front, and then, some breakdown that contains all the slip and of course, slip-dependent energy that's being dissipated. So that was this kind of discrimination. I think that Federica at least was suggesting that this fracture energy then is scale independent. Now, the question I'm asking myself is whether that is a valid assumption, or whether it is at odds with observations that we have since almost 30 years, suggesting in the field and partially also in the lab that the process zone does not necessarily have a constant size, which basically is a geometric measure of the fracture energy that's being dissipated. Doesn't matter how complicated. Yeah. So, I mean, Chris Schultz would argue that you have a scaling with the length of your rupture that implies a larger zone of which you dissipate energy during the breakdown process. And he shows field evidence. Maninghetti shows field evidence. I think Onaka argues in the same direction. So that is the question that I'm asking myself.
I could just make a comment on originally I interpreted this as possibly the heterogeneities or these strength barriers in the lab are just less prevalent. As you go upscale, you have more variability or more barriers due to kind of roughness or jogs or something. And our planar faults in a lot of these cases in the lab are very thin, smooth sections with small HRMS roughness. But I'm also on the boat that these models aren't the best way to look at it. So I'm kind of trying to understand how the scaling of the heterogeneity and strength, let's say, that would be these barriers and affect the rupture process zone and increase GC with size, how this varies from lab to larger regional scales.
Well, Onaka has made a suggestion that I think has some credibility, that the kind of defects that you activate when you form a larger and larger rupture, a larger and larger fault, when the fault grows, that you encounter larger and larger defects because they're parallel distributed. And therefore, if your patch size, your critical slip distance scales with that roughness, you would expect that your energy does indeed increase.
Yeah, and this is, Georg, to me, this is exactly the effect of the breakdown zone. Onaka was interpreting this exactly as an effect of the breakdown zone, of the deep dependence that you have inside the breakdown zone.
Well, I think, you know, going back to what we heard yesterday, but, you know, it's entirely possible that I completely misunderstood what Federica and David and probably also Jay were after. You have the rupture front that is associated with, you know, breakdown at the tip of the rupture front, which is a fracture process, and that is scale invariant. That energy is scale invariant. It's a material specific number. Now, then the breakdown continues because you have associated slip that is lagging behind. So it's this frictional tail that is sort of, you know, lagging behind. And that, of course, is not scale independent. That's scale dependent. And so these are two, for me at least, two conceptually different models. And what I'm trying to say, because it's already 30 years ago, so people may not necessarily remember, there is some evidence that lends credibility to this first model, that actually the process zone increases, meaning that the energy, the fracture energy, has to increase at the tip.
Georg, can you remind us what that evidence is briefly?
Yeah, that's like, you know, a whole series of PhD theses that were done by students from Chris Schultz. There's a work from Isabella Manning-Getty together with Geoffrey King, who looked at, you know, displacement length scaling of faults.
They are quasi-static cracks. The Manning-Getty were quasi-static cracks that are not appropriate for an earthquake that is radiating seismic waves.
Well, I mean, they were basically looking at geological outcrops.
But it is a quasi-static representation.
Well, I would assume that
here we have seismic waves, so quasi-static description does not work. For
no. I disagree, because you know, these faults were presumably formed and presumably grew also by a succession of seismic events. I just refer to the whole body of work that Chris and other people did there. Okay.
So can I suggest to keep this discussion for the plenary concluding discussion? So I see that there are questions by Rachel and Nadia that are perhaps to Paul or to the seismological estimates, because we have 5 minutes to close the session. So Rachel, please.
I'm not quite sure where my question fits into all of this, but you probably realized I'm a bit doubtful about using these sort of bolt, rough, simple model estimates of energy and stress drop or whatever to measure the dynamics of the fracture. But what has struck me over the years is how variable earthquakes are on very small scales. So it's not that you can go to, you know, this region in New Zealand or that bit of the San Andreas Fault or these earthquakes in, you know, the eastern US, and you will get a strong difference in the average properties. You get much bigger differences on length scales of, you know, hundreds of meters to kilometers. I mean, it's our resolution that's limiting us, I think. And that's where we're seeing really big differences between the frequency content, the radiation of the earthquakes. Now, either, you know, you can argue how much of that is the actual earthquake itself and how much of it is, you know, local variations in attenuation or material properties or whatever, but it's basically small scale heterogeneity is having a really big effect, much bigger than any sort of, you know, might expect these larger scale things to be having. And I just wonder, you know, how we can use that to learn more about what's controlling the dynamics of rupture, both at the small scale and the large scale. General question to anybody.
Nadia?
Yeah, thank you, Rachel. I have something I think that perhaps will intersect with that, but first, since we're talking about seismological, you know, estimates, just want to point out, I don't know whether it was mentioned, I'm sorry that I couldn't attend the entire workshop, but many of the seismological estimates, and Rachel can correct me, you know, if I'm wrong, for large earthquakes, right, are done by sort of assuming what the radiated energy is, right? So you have a model and you get out of that model some notion of available energy, which is somehow governs things, and then you subtract radiated energy from that. And I just wanted to point out that we don't fully know what the radiated energy is, right? So just to give an example, the Abercrombie and Rice work considers a crack-like rupture, right? And it has one, different scaling, and then they subtract radiated energy and get some breakdown work. And then Vieska and Garagash and their work assumed a pulse-like model that creates a different available energy. They subtracted the same radiated energies, seismologically found from that, and found, an order of magnitude larger breakdown work for some events, right? And so that means that it's, it's important what the radiated energy is. And we have some evidence by comparing teleseismic and regional estimates of radiated energy that we don't really know fully what the radiated energy is, right? So if you take crustal earthquakes and you compare radiated energy obtained teleseismically and regionally, they can differ almost by an order of magnitude themselves. So you can have 5-6 times variations. I can share and plot and show, but I don't have to do that. And so for largest earthquakes, it's not, and so radiated energy would then differ also depending on which model you assume and which frequency you take into account, and so on and so forth, and whether you have, regional data or not. And for most earthquakes, we don't. So of course, radiated energy estimates are teleseismic and potentially lower. So I just wanted, from the seismological observation point of view, to highlight that as, and so close observations, like on a field scale, or earthquakes that have regional data, perhaps can help us solve this issue.
Nadia, I fully agree with you. And it is also important to remind that when we play the game plotting the radiated energy on the slip weakening curve, this is valid on a point source. Okay, so all the discussion on heterogeneity, rupture from propagation does not work because radiated energy cannot be mapped on the full plane. Radiated energy is a global estimate of energy, it's not a work rate. So every time that we play the game with this picture, everything is fine, but this is the simplistic representation of the problem.
Right.
On the other side, measures of fracture energy done with the point source scale and agree with those done from dynamics and extended source that do not assume at all the radiated energy. So you are perfectly right, but it is really a complex approach. But I fully agree. Good point that you made.
Right, and then to something that Rachel said. Again, maybe this was already mentioned, but there's this thinking, right? I mean, it's easy to think about breakdown as being slip dependent, right? And then you have linear slip weakening, non-linear slip weakening, other slip weakening things. But we know that friction can be, or resistance in general, not just friction, breakdown of all sorts, can be slip rate dependent, right? Inelastic processes are strain rate dependent, and so on and so forth. So even if you sort of do the bulk processes and put them into this breakdown work, they all can also be rate dependent. And so what we found in the lab recently, right, is just we put a little bit of a gouge layer and had the rupture try to rupture through it on, on otherwise homolite interface. And because the gouge has very strongly rate dependent, properties, it's rate strengthening at low slip rates and it's rate weakening at high slip rates. It is ruptured, but it is ruptured through this process when the resistance goes up and then falls down, and then goes up and then falls down, and goes up and then falls down, and the slip rate does the same. And these are not like 3 different events. It's the same dynamic event, and the actual overall rupture speed is about like 0.7 of the shear wave speed or something like that. So you don't have a nice breakdown with slip, right? With slip, the resistance goes up and down, and it's very hard to know, right, how to estimate anything close to breakdown work of fracture energy in that context, because you do not have a bottom, you don't have a minimum in friction to which you can go. You don't have a steady fields around the crack tip to try and fit any kind of, theory, right, to it, especially not one with the constant things. And so it's the same in modeling, right? Once you assume a fold that has a rate dependent something, and then some heterogeneity, which obviously that gouge probably has, it's going to go up and down. And so it's not entirely clear how to even think, about defining fracture energy other than just say, here is some dissipated energy in there. So I just wanted to highlight that the slip rate may matter, or the rate of this breakdown may matter. And as it varies, which it can do by orders of magnitude, right? Or 2 orders, even from something like 0.1 meters per second to 10. And the resistance can be going up and down. And just for myself, I'm even thinking, how do I compute the relevant quantity, right, that governs the crack propagation in that case? I can imagine modeling this with linear slip weakening and finding an effective, right, fracture energy that would allow me to get the same average rupture speed, because the rupture speed is sort of intermittent. But other than that, right, it's kind of what Rachel described, right? There is this complexity, even in these very small laboratory samples. Also, to very nice talk by Paul, that is not entirely clear how to interpret even on the smaller scale.
Yeah, exactly, I agree. So thank you, Nadia. I think that we can close, Chris and others, the session. Now, I think that we scheduled in the program half an hour for discussion, but before opening the discussion overall for concluding remarks, I think that we have to recover some presentations from yesterday. So Chris, Men-Andrin, I give the floor to you, and I ask to the listed presenters to start.
Yeah, very good. And lots of great comments, lots of good things to start to think about, to discuss. There are 4 people who have told us they would like to present something. And Francois Pesseleg, I believe, is one of them. And if you are ready, maybe that would be a good place to start, Francois. I don't see him rising. I know also.
Yes.
Okay.
Sorry, I can. It's a bit similar to what Federica presented yesterday. So maybe if you don't have any time, I don't know.
Sorry, I didn't hear.
I can. Can you hear me? Okay. No, I was saying that it's a bit similar to what Federica's presented yesterday. So if you don't have time, if we are missing time, I can skip.
Yeah. Okay. Look, time's always of essence, but you're talking. So if you want to present something, do, and if you just want to make a point verbally, do that. But let's keep these. There's four of them plus, and let's keep them to just a minute or two to generate a discussion.
Okay, so I just wanted to start by this slide, in fact, because yesterday we talked a bit about that. So what do we know from laboratory earthquakes in terms of fracture energy? So this is the results that we published, in fact, with Alex Schnell, Stefanisson, and a lot of other people a long time ago, where in fact we are doing stick slip experiments using rock samples, Western granite. And in this case, in fact, we're able to have an estimate of the fracture energy as a function of slip. And what we saw is that, in fact, assuming the hypothesis we made, we had the scaling of the fracture energy or breakdown work was scaling with a power 2 exponent with seismic slip. So I think with the step back I have now, I will do a bit differently to estimate this fracture energy, because probably we are biased a bit by the way we're using the estimate of DC. And I think also in this kind of experiments, slip in rocks, for instance, such scaling are a bit biased, in fact, by the stiffness of the apparatus. However, it looks that it provides an estimate, and it's what we can do up to now. So what we did recently, with Federica, I cannot see the figure, it's not good. It doesn't work. Why? Okay, I have a problem, but I don't know why. Well, anyway, so I don't know if you see.
You can enlarge the preview. You can try to enlarge the preview.
Yes. You cannot see the image, or can you?
No.
No, we don't.
No,
we
okay.
Don't
well, if you remind, in fact, what people have seen yesterday, using the stress singularity at the tip, in fact, it's possible to fit with LEFM or cohesive zone and have an estimate of the fracture energy. And the piece I wanted to say on that thing is that a lot of people did it. And it's working in some experiments in the lab, mostly when in fact the rupture length is larger than these parameters. That's the function of the cohesive zone. So in most of experiments, in fact, at the scale laboratory, you can explain and have an estimate of the fracture energy because of that. And as Federica has shown yesterday, in some other case, in fact, what we have seen at the scale of the laboratory is that we have different, let's say, cohesive distance and probably related to different weakening mechanism. But in this case also, in fact, you can still have an estimate of the fracture energy from LEFM. However, in that case, the fracture energy will be not only a function of the first weakening, but also of the second large-scale long-tail weakening, as we call the long-tail weakening. And however, if the rupture length is larger than this second cohesive zone and multiplied by the modulus divided by the shear stress, you can recover the square root singular fields, and you can still describe the rupture tip, the singular fields of the rupture tip using LEFM. So, however, it's not the case for all experiments, and as we have seen yesterday, sometimes the residual stress never reach residual value, and so you have a continuous weakening. And in such case, in fact, I don't have any pictures, so I don't know why. The LEFM is not adapted to describe and predict the singular fields. And so you have to modify, in fact, the square root singularity, as people have done from Beder and Burbinder. And also, it's something that was known in hydraulic fracture mechanics. And also in other modeling using thermal weakening, such as thermal pressurization and flash heating. So I'm sorry, really sorry, there is absolutely no graphs here. I don't know why at all. So I think I will finish it here because it's.
Okay, yeah, great point. And if there are some
really
comments,
I don't know why.
Directly on this. If there's some comments directly on this, please, yeah, raise your hand. Let's stick on top, otherwise we'll go to another presentation and then come back. Okay, think about it. And David Kammer also wanted to make a brief point. So let's go to David, and then Stefan Nielsen, if you're okay, right after David, we'll go to you, and then to you, Georg, if that's okay with everyone.
Yeah, sounds good. Mine should be really brief. I just wanted to basically give a little spoiler to Huey's talk he's giving in this seminar series next Monday. Actually, I think what this brings together is a few things that we just discussed before, and I think it could be one answer it is a possibility. So since we have seen this, this graph of the scaling of what I now definitely would call breakdown energy, to be sure that we distinguish it from fracture energy, and has been discussed before. I also want to show this sort of like going back to what Rachel says of being very careful about interpretation of this. And I think what we showed in this recent paper actually points to that as well. And I want to just quickly explain that. So we did a very short model, a very simple model, 3D self-similar model. But the key is here that we really imposed a scale-independent fracture energy in all our models of different size. And the only complicated thing is that we had a non-uniform stress, which then was scaled from one case to the other. And I think this actually would also explain what Georg just mentioned a few minutes ago about heterogeneous being responsible for arrest. Actually, that's one way an earthquake could arrest. But there is a second way, which is if the earthquake runs out of energy that is driving it. And so this model could actually give the reason why a rate-dependent weakening of friction, where you have first the fracture energy and then continuous slow weakening, as suggested by previous discussions here, could still work with arrest and with scaling of the earthquakes. So I think this actually brings both sides together. And if you run this model, what we observed is that the stress overshoot is scale independent and non-zero in these models. And if you make this assumption, actually, this adds a corrective term into the calculation of this inferred breakdown energy. And here we have the fracture energy. And then you have an additional part here due to this stress overshoot. And usually that is being neglected for various reasons. That's fine. But in this case, if we put this very simple model, this one cannot be neglected. And if you add it on top, you actually recover the scaling that is out of this data from Abercrombie and Rice. And so we can show that this can be the result of the overshoot. Now, by no means I want to argue that our model is the most realistic and that this is how it should be or so, but I think at least it shows that but if we interpret the seismic data as an indicator for continuous weakening, secondary weakening, whatever way you want to interpret it, this is the counterexample. You don't have it in a model and still can recover this behavior. So as in math, we would say this is proof by counterexample that this data is no indicator for continuous weakening at the fault. So this is just so much averaged, and the energies, as Nadia pointed out, the radiated energy is not very well constrained and so on. I think we just want to point to the fact that we have to be very careful. And that's all I wanted to add.
David, that was fabulous. Thank you very much for advertising that talk. You know, Chinyu is with us. And so before we even go to Massimo's question, I want to give Chinyu, also goes by Huey, the floor to say a few things and maybe answer Massimo's question if he's got one. So Chinyu.
Yes, regarding to that research, I also want to answer the question in the chat going on right now. So the question is, what is the source of that scaling? Why do we see these scaling in the breakdown zone? So one possibility is simply that if you have a larger earthquake, then you need to propagate into this unfavored stress region further in order to stop it. So that scaling can just solely comes from how big the earthquake is and how much the energy has been really released. And so from our Nature Communications paper that recently just got published, we have two cases of stress, non-uniform stress. One is similar, the other is not. The other is simply a step into low stress state. And we see very similar scaling. So I hope that answers the question in the chat. And yes, that's what I want to say. Thank you.
Thank you very much. You're very good at multitasking, better than me. Massimo, you're going to make a point, and then Lisa.
Yeah, I want just to make a comment to David that in general, if we measure the breakdown work for the model that you presented, the breakdown work would not include what you have put in the undershoot, because in that case, this belongs to frictional heating, because it is below the minimum stress.
Exactly, but yeah, I agree with you. It's not the breakdown energy, but it's the inferred one. If you do the process that is done with the seismic data, you would actually include that by error, because you cannot know how much it is, right? So it is being neglected. And so, yes, it is not the breakdown energy that we have, but the inferred, that's the keyword actually there.
Lisa.
Okay, I have two questions. The first one is, with the DC that is around micrometers, seems to be 10 micrometers that you used, are you not reaching the super shear raptor velocity? Are you sure? In any, or it depends on the stress drop you're using that is in the boundary to have a sub shear, because it's very small for larger events in the homogeneous condition.
Yes, but it also depends on the stress drop, and so we don't have super shear. You can have super shear if you want, but these none of them that we showed were super shear.
Yes, but 10 micrometers for deep weakening low in a fault that is large, like 10 kilometers. I cannot believe that you can have a sub shear rupture, or you have a very small stress drop and you cannot allow any larger stress drop, larger than 10.
I guess you I guess you has the better answer, but I.
Oh, I'm sorry. I was looking at the chat.
So it is. I know it's not super sure for sure, and you can put in what you want to actually. So if I put back the slides, maybe for just a second, if you allow.
Yeah, go ahead, David.
Yes, sorry. Right. So you're saying here, if you see it.
Mm-hmm. Yeah.
Right. So actually, the simulations that you see here, we simulated until here. And you can see that we have a stress drop, average stress drop of 1 megapascal, which is a reasonable stress drop. And the fracture energy we imposed is this, the 100 joules per mega square, per meter square. You probably are better in math that you deduced the slip weakening distance. But this is what we have. The data is even online. We pushed all the data online, so anyone can look at them. Yes, and they're.
I'm not saying that
separated.
it's not true. No, because
Yeah.
I only say that maybe you have to be forced to use this kind of 1 megapascal, nothing more. Otherwise, you can fall in the supershear raptor.
We just chose, we chose a value that is which fits what you see in the Earth, essentially orders of magnitude, right? That's what you see there.
Another question is concerning your computation of breakdown energy with the orange rectangular area. This is done during the stopping phase. So what Massimo was saying is that this different from the definition of breakdown work, but this is not a problem. But in any case, from a seismological point of view, you are not seeing nothing because the slip is stopped. So how you can say that this is what people from seismological point of view can see this kind of orange?
Whether they can't, I think, I'm sorry, I'm a civil engineer, so I might not exactly know, but at least from my understanding is you cannot distinguish between the final and what you have as a residual friction, right? So in our case, the imposed one is residual, and then the final one you go down here because of stopping of the arrest, and I guess you would only see the final one, but you don't see the residual. That's my interpretation. But at least the model, when you compute this, doesn't account for it, right? It's like when you go and compute the energy, the inferred fracture, the inferred breakdown energy, there is no way of including this immediately unless you take into account it the way we did here. And we didn't invent this equation. We're just reusing it and put the values in that we found from the simulations. I don't want to take credit for someone else's work.
Thanks.
Stay on this topic and go ahead very quickly before we go to Nadia's question.
Oh yeah, I just want to add that on that note that in Abercrombie and Rice 2005, they also mentioned that the final stress has to be equals to residual stress, otherwise you'll have a bias. And that's because when you are calculating the available energy, the release energy is comparing, it's a function of initial stress and final stress. And of course, you can average that using the Noda and Lepustat method. It's this energy averaging method, and that'll be still the same. So yes, that bias will exist whenever the final stress is not equal to the residual stress, which can happen for crack-like rupture and also for pulse-like rupture, but in a different direction.
Okay, that's great. Nadia, we're going to go to your question, and then let's switch to another subtopic, let's say, because Nielsen wants to present something, and we're going to come back to this on Monday. So we're going to have a much more extensive discussion of this on Monday for Chinyu's talk. Nadia.
So David, very interesting presentation. I missed, were these numerical simulations that you actually simulate all these different ruptures? So what were the rupture speeds?
Sub-Rayleigh, standard sub-Rayleigh rupture speeds.
You know, because one way to think about, right, this increase in fracture energy, it doesn't account for all of it, is to say, you know, if you go by observations, right, you want to have average rupture speed to be something like 0.8 of the shear wave speed, not really completely limiting, right, not at 0.8 you know, not like 1% lower than the Rayleigh wave speed if it's a mode 2, but sort of 10% lower. And as the rupture gets bigger, right, for, you know, you need more and larger fracture energy to keep, you know, to keep it from accelerating to the limiting speed. So I think that's one of the ways, right, in simple cases to distinguish between what is the so-called fracture energy and what is, you know, just fracture energy or breakdown energy plus something else, right? So do you get this? Are your ruptures all at something like on average 0.8 of the limiting speed, or do they actually accelerate to the limiting speed? Because I think that refers to what Elisa was asking, right? Like if you want to keep the rupture, like if you want to match seismic observations, right, then the difference between 0.8 and 0.9 of the limiting speed would be noticeable, right? And larger fracture energy in dynamic simulations of real earthquakes helps to, you know, accomplish that, right? To account for all sorts of things that would make large earthquakes still not limiting speed.
So thank you for this question. I don't know the exact speeds you would know, but you can think of it, it's a very simple model. The fracture energy is constant, which it may not be in nature, right? That's not what we are claiming. I'm trying to make a point that we don't necessarily need to see the scaling that is observed in the inferred scaling. Right. Since everything is uniform until we get into the arrest zone, the rupture follows what you would have from an equation of motion of a brittle crack.
Right.
But if you want what you're suggesting, if you add a little bit of additional increase of fracture energy with speed to stabilize it at the lower speed, we could do that. But I don't think the point is you would have a scaling of the fracture energy over maybe an order of magnitude or something, but you don't recover 8 orders of magnitude as seen in the seismologically inferred values, right? And you would still then get the same by going through the averaging process they do. You would recover this behavior, maybe even a little bit steeper because you would have the actual increase of the fracture energy that you suggested.
But also if you keep the rupture slower, David, then you're going to have, I think, I'm not, you know, it's a long time since I've done, you know, these crack-like simulations, but if you keep the rupture slower, you'll have a lower undershoot. So, you know, it's not just as simple as everything else will stay the same. So, for example, you know, so it's going to be then complicated where the undershoot will also change if you start changing the rupture dynamics. And so you may or may not have that scale in the spectacular way with the rupture, because, you know, you have the same essential dynamic resistance. Larger ruptures are faster and happier and accumulate more slip. And by the time they arrest, the fault realizes it slipped much more than the dynamic resistance, and you have an increasingly larger, you know, overshoot, right, or whatever that is called, right? And so, and then you have the scaling. As you start messing with the rupture dynamics, that will change also. And I'm just curious in which way, because we do have this observation, right, for the rupture.
Yes, in fact, before I was wrong on the slide, I was saying we see the stress drop, but it's actually the overshoot. So we had an overshoot of 1 megapascal, and the line below was 0.1, 1 order of magnitude lower, and you still get the scaling. We're just slightly parallel below. So even if we go slower and we would reduce the overshoot by an order of magnitude, right, we still get the inferred, or we would still see a scaling in the inferred version of the breakdown energy.
That very well may be. I'm just wondering how it will all work out, right? Because in fact, then the shoot may disappear. That's what I'm saying, right? Or even turn into a mild, you know, overshoot the other way, right? Because crack-like ruptures can also, you know, have, you know, they're not pulse-like, but they can have, they don't have to have an overshoot in general. I'm just asking.
In fact, no, and it's a good point. Actually, in the appendix of our paper, and this is Greg's thing, we did actually just randomly chose values and then plotted it on a log-log plot. And you still get a very similar scaling macroscopically observes by just randomly picking an overshoot that even goes, becomes an undershoot. And then the undershoot data doesn't appear because it's a log-log plot, and all the overshoot data points get on the same scaling because you're, due to the log-log plot, you like squeeze it together on a line. So I think that would make that point a little, to some degree.
No, I agree. I agree that the trend, I'm not convinced in the observational trend myself. I'm just pointing out.
Yeah, thank you. No, I'm
great
appreciate the discussion.
Great discussion to continue on Monday. Stefan Nielsen, you wanted to talk about something, please do.
Yeah, thank you. You just 2 minutes reconnected. And so there are so many interesting things to talk about. So I'm just trying to be brief. This connects a little bit to the talk we had yesterday, the discussion we had yesterday. And can I share my screen quickly? So I prepared this slide. Don't take this too seriously. This is just meant to make sure we're all on the same basis as terms, because some terms are confusing, especially when you try to establish dialogue or an understanding between people who are working in slightly different disciplines. And I think this is particularly between physics and geology and seismology, which are, for me, things that use similar terms in different ways or different terms for the same things. And so Chris was saying earlier, I don't understand your poll. Should I be in one camp or the other? I don't think there's any reason for choosing one camp. I think I put 2 columns here, which for me are, in my opinion, and my current understanding of the problem, are more or less equivalent and both acceptable. But the point is that I think for convenience, we use the word friction to describe a large number of things, and maybe it's a lack of rigor. But what I often intend by friction is, as Nadia was mentioning earlier, it's not only friction, it's any process that will produce weakening in the material. And we call it friction for convenience again. What we do in the lab oftentimes induces very, very extreme and violent conditions where you have melting, decomposition, cavitation, fracturing, and all sorts of stuff. Can we call that friction? Well, depends on what scale we're looking at. And I think also Francois earlier made a point, although his graphics didn't show very well, I think it was quite clear. It's the scale at which you observe the process is very important. If the process happens in a very, very small region close to crack fracture tip, then you go back into the linear elastic mechanics theory, and that's fine. If it's on a larger scale, maybe not. In both cases, I think that you have a strength drop. So a physicist call it plasticity. Plasticity for geologists is quite different things, because it involves crystal plasticity, dislocation creep, and these kind of things. But plastic processes, which mean an elastic process in general, can be quite broader. That's what happens at the fracture tip. If we look at the large scale, which is not the thickness of shear, we can interpret it as friction because it's a macroscopic behavior. Now, if you don't like the word friction, you can use something else. But then, as a joke, I put disagree or disagree checkbox at the bottom. you can all try to fit, and I would check both agree box on this. And that's all. Just a short point. Thank you.
Okay. Great. Well, I assume the chat's going to be blowing up with people's choices here any minute, so I'll let them, unless somebody wants to make a point or comment about this.
Yeah, if I may.
And then, yeah, go ahead, please.
Yeah, okay. So Stefan, I think we're talking in rocks about breakdown zone sizes or process zone sizes of a finite length. So it's not infinitely small. We are not fracturing glass.
Yes, yes, a quick word about this. One thing that people like, well, a long time ago when people started doing rupture models, they realized that if the rupture goes very fast, the process zone can shrink to an infinitesimal size. Well, that doesn't happen very often because ruptures usually go slower than the Rayleigh wave velocity. Well, there's then the whole point of super shear ruptures, and it gets really complicated there. So usually, I agree with you, the process zone is not microscopic in earthquakes, although in theory it could get very small if rupture starts to propagate very fast. But I believe, as you mentioned, that it's quite big. It's probably a good percentage of the rupture length.
Well,
But
I mean,
I believe that it will increase with the rupture length.
Sorry when I interrupt. I mean, even if you look at impact experiments, yeah. So you know, when you test armor, for example, with cannons, then what's left behind is a process zone that is related to that impact. You know.
Sorry, I'm muted. Yes. So.
I'm not sure if you can get faster than that.
Oh, you mean the shock waves and the deformation due to shock waves?
Yeah, the deformation due to shock waves.
So yes, so what's the?
Yeah,
so yes, I agree with that. I don't see the, I don't see the problem.
Yeah, no. I mean, theoretically, I think you're right, but what we see as a sort of a documentation is the damage that's associated with the propagation of a dynamic rupture, and that is finite, is a finite zone.
Yes,
absolutely. I mean, we see it in experiments, and we see it in, it's not infinitesimally small.
Well, no, it's never infinitesimally small, of course, but the whole thing is, I think the point that Francois was making is that if it's small enough compared to the length of the rupture, then the nature of the stress field falls back in linear elastic mechanics, and you can define all those things like fracture energy in the classic way. Now, I don't know how small it needs to be to produce that. If it's not small enough, then it's very difficult to analyze it in linear mechanics. But yeah, I mean, I agree with you. I think it's extended in the case of earthquakes. I don't think it's an infinitesimal zone, but some may not agree with that.
Okay, let's get Nadia's point, and then Georg, you want to present something, so they're going to come right back to you.
Yeah, I just want to put myself in I agree box and on Stefan's slides. And like I said in the chat, I increasingly try to replace friction or frictional resistance with shear resistance, just to emphasize that, you know, it's sort of kind of like friction, because lots of measurements from the lab have some of these processes be sort of approximately proportional to normal stress, right? But so in that sense, we like to say friction, right? But it's clear that a lot of things, even in what we call friction, right, combine like things localized, delocalized, break on local scale, right? And by the time you add some, you know, the process zone that's probably bulk-like into friction, then it's the plasticity that Stefan mentions and so on. So I think I just want to second this notion that, you know, it's not just friction, of course. And also that to this discussion of the size of the processing zone, just to reiterate, you know, the processing zone, you know, I do believe that we may have very rapid drops, and in that sense in friction, and then in that sense, or resistance, and then in that sense the processing zone can be very narrow, but it's probably intermittent, right? And so I think one of the difficulty, like even if it's an extended one, it's not entirely clear to me that it will start with the peak and go to the minimum, right? And then it will be difficult in models like these, when you include heterogeneity, it's very difficult to compare with linear elastic fields, because, you know, the thing is non-steady and, you know, non-conventional. So so even if it's locally small, there could be like several of them, one after the other. So
yeah, really good point, right? Whether it's normal stress dependent is what we call friction, but here we're just talking about strength of a contact, right? Yeah. Georg, and then everyone, the plan would be to try to finish in, let's say, 10 or 15 minutes at the most, to retain some energy for the next time that we meet. Georg.
See my screen? Can you see my screen?
Yes. Yes.
Yeah. Okay. So I changed my slides due to Jay's nice presentation and comments yesterday. So, and this fits into, I guess, what Nadia just said, right? And also it gives me an opportunity to bring up some memories with some of you that joined this workshop here. So this is a slide that I actually owe to Zev when he guided a field trip to a mine 1,400 meter deep that just had experienced an earthquake, 5.1. And we got a very interesting Structural Geology 101 lecture by him while loose rocks were hanging on top of us. And what you see here, and this is why I find this interesting, is you have the fault here that has been activated. And at least 3 of these shear bands in that fault zone have been activated. We don't know simultaneously or sequentially. And we know this because there were rock bolts here that were sheared off. Okay, so it's actually quite a complex rupture that affects an entire volume. It's not just, a planar dislocation in an elastic half space. And this is another nice memory that I like to share with you. This is a visit, a field trip that we did with here, Chris, for example. It was organized by Massimo, and we're sort of walking across the fault hanging wall, footwall of the Gubbio fault that had experienced, I think 20 years before or 25 years before, a 5.3 earthquake. And what you see here is, and what we marvel at, is this enormous topography and roughness that we see, okay? So again, it's definitely not a planar contact. Now, when we want to investigate things like this in the lab, we perform fracture experiments, and then we have a fault that is rough. And then we look at stick slip, which we did here at elevated confining pressure, 150 MPa. All the green dots are acoustic emissions, and these yellow dots are the large events that are associated typically with the initiation of the slip event. And so when we try to calculate the rupture velocities, they are in these kind of experiments between 10 and 100 meter per second maximum. And so this thing has seen, I think, up to 5 stick slip events. And what you see here is a computer tomograph image. And then when we blow up, say, this region here, if you see my cursor, this is what we find. So we have these bands here that show enormous comminution, which is associated with the slip, of course. And we have these lenses that form the asperities in which we locate some of these really large acoustic emissions. And they show all sorts of, shear and tensile fractures. So significant amount of damage. And honestly, it's not clear to me, coming back to this point from Jay yesterday. So you have a rupture front, of course, and it has nothing to do with a frictional tail because it's like 3 orders, 4 orders faster than the slip that may occur there. But I'm not absolutely clear whether this frictional contacts that you have here that are slipping don't affect the fracture process in these lenses. And when you blow up this even further, you see the displacements here of mineral fragments that are associated with the rupturing of this asperity. So that's basically what I wanted to share with you briefly.
Really nice. Yeah, interesting to see the complexity.
So it's not a planar surface, and the kind of roughness that we produce in the lab is of course way smaller than the roughness that on which you were stepping around on the Gubbio fault in nature, and that is even just the roughness of the surface. It doesn't even include roughness that on an even larger scale you may have due to the coalescence of fault segments that have stepovers.
Good point. Massimo.
Yeah, Georg, I thank you for pointing out this and actually to bringing us back to the origin of the workshop, that was to reconcile our interpretation with the geological observations and also with the seismological and instrumental observation in the lab. So yesterday there was a discussion, and there was also some further discussion in the chat So it is clear that if we look to what you presented and what also presented Dan on the first day, on Monday, it is clear that what we call constitutive law. So if we look at the way in which the shear stress is evolving during the earthquake, which is the shear evolution with sleep, we should formulate the constitutive law in terms of strain and strain rate. And perhaps there is a critical strain where there is the switch to strong localization. We are unable to do that. And every time that we do this, we transform the strain as sleep divided by thickness, the strain rate, sleep velocity divided by thickness. We do not control the thickness, and our law became dependent on sleep velocity. So that's, to me, what you pointed out is not the answer to the questions between fracture and friction or fracture and rupture. To me, this is exactly what is the real limitation to understand the evolution of shear stress with time, sleep, and other parameters, which is the constitutive laws, is behind because the energy is there. So the stress will evolve as the way in which the energy will be released. So forget the models, but if we look at reality. So to me, you really focus on which is our difficulties to explain, especially for a thick fault zone. And therefore, depending on the stiffness and the cohesion of this thick fault zone, we can have a completely different response. You can have some cases in which you have a porous, like Alexis showed yesterday, and Dan showed when he showed us the faults with low porosity. We can have multiple principal slipping zones that can even slip together, or you can have an intense strain localization on a single shear band, and therefore at the micro scale you have these processes, but at the macro scale you see the shearing. So to me, what you presented is exactly, and we are struggling against these limitations, the difficulties to explain the constitutive law in terms of strain and strain rate.
Yeah. Okay. I think Jay had a comment.
Yeah, I thought he did too.
I don't want to talk too much, so I'll make this very brief, although I've talked a lot anyway. First of all, I'm fine with both Stefan's point and with this comminution thing. Like I said, I don't believe that an earthquake happens at 10 microns wide slip zone. So we have to somehow find out whether the comminution and stuff that does happen, does it happen during the passage of the rupture, or is it some residual dissipation that happens afterwards? And if it's happening during the rupture, it's just part of the cohesive zone, in my opinion. If it's afterwards, if it's too far afterwards, it's settling of the system, but it's not clearly related to the earthquake dynamics. But that's all I had to say. Thanks.
Okay.
Good points. Nadia, and then Valère. Oh, I'm sorry, no, Valère, then Nadia.
Yeah, I was just gonna say Valère, yeah.
Fine, all right. I guess I just wanted to follow on that with the thought that I've been having throughout this workshop. We talked about, there are different processes involved in this overall breakdown process, and there's kind of this idea of maybe we can separate out some portion that is more local, and that can be our fracture energy control, presumably the component that's controlling the rupture propagation, similar to cohesive models, and the rest of this residual breakdown, right? But I just want to make the point that what's happening in this breakdown process still does matter. It's not necessarily a local property, but it's a global property, right? And that's an important aspect here. So if you have continued weakening, how that change in your potential energy, if it goes into dissipation or energy release driving the rupture forward, will change the rupture speed, right? Similarly, if you have re-strengthening, you can arrest slip, which also changes the overall energy release, right? So this other component that might not be localized at the rupture front still is important for the overall dynamics, which I think is complicated. It's similar if you think about which is crack branching for dynamic fracture and limiting the rupture speed there, where you have fracturing behind the crack tip, right? So it's just kind of this point that this is the limitation of the cohesive zone model in itself, right? Even if you have dissipation not at the crack tip, it can still have higher order effects that affect the rupture propagation. So I don't think we want to necessarily disregard everything that's happening behind the crack tip. It's just complicating the story.
Could I answer?
Please.
Okay, so I was showing this picture from the mine because I found this incredibly interesting to see that we can document that whatever happened there as a rupture involved the activation of at least 3 surfaces. Okay, so it's not that you could I mean, of course, theoretically you can break it down to one narrow fracture tip, but in fact we have an involvement of 3 of these planes. We cannot discriminate whether they were activated simultaneously or whether they were activated in some sort of a sequence, but they clearly were all involved. Now, if let's say you would have just a thought experiment, if you would have a rupture going across one of these planes, and then later on another one, I have a hard time to believe that the frictional tail that is associated with the first rupture does not affect the rupture on the other planes, okay, in this entire process.
Thank you. Nadia. And then we're going to close.
Yeah, I just wanted to say that what's at the rupture front and how far are you behind the rupture front is significantly different in 2D and 3D. I think we have been thinking too much, maybe myself included, about 2D, right? That's what's easiest to do in the lab. And so if you have a crack front, of course, the transit, 0.8 of the shear wave speed, there's only so much behind the crack front that can affect what happens at that 2D crack front. But if you're in 3D, right, and you are having rupture spread in one direction, and then maybe the stress is not so favorable in the orthogonal direction, but then some additional weakening happens even far from the crack front, and then affects that other rupture front, which is going perpendicular, then these are the kind of effects, right, where it's difficult to separate where the weakening, and the loading is only local, or it comes from the back of one rupture front to a nearby orthogonally going rupture front, and so on. And I also agree with the sentiment expressed that in models very often, right, in heterogeneous, especially if you have a lot of slip somewhere, then fronts go backwards, then there are rupture parts of the fault, and that would be another case where, I don't know how often that happens in nature in large earthquakes, but that would be another case where, right, the back of the crack front would matter more than in a 2D, simple model. So, but more, I find in 3D models especially, which are sort of difficult to run, that the weakening at the far away from the crack front affects the rupture dynamics by affecting, the 3D nature of it. So it's something to think about. Yeah, 3D versus 2D, I think.
Beautiful. Thank you. I am going to share my screen and ask you to unmute and join me in thanking Massimo. Really, Massimo did all the work in organizing this because, I don't know, it's just Massimo. I don't know about you, but I hear constantly about people talking about how it's impossible to focus online, and there's so many distractions, and there's just a bunch of things going on. And I think we just the last few days proved that to be completely wrong, at least in this situation. Lots of focus from people, great comments, and really a fabulous discussion. So hats off to Massimo. I'll leave Massimo to the last comments that anyone's going to make.
My last comment is simply, I thank all of you. It has been really exciting, stimulating, an excellent opportunity. And in my opinion, now we should try to have a meeting in person next year. So to have the possibility to have 3 days, perhaps in some places when we can have marsala or wine, therefore we don't need to drink the J bottle, but we can find that over there. So I think that we will try to figure out how to manage this, and I hope that also the situation will be improving so that we can travel and stay together without any pressure.
Beautiful, and thank you for organizing that, Massimo.
Yeah, thank you, everyone. Thanks, excellent.